Hello, calculus students. Math 201, looking at section 2.6. Limits involving infinity and asymptotes of graphs. All right, in this section, we investigate the behavior of a function when the magnitude of the independent variable x becomes increasingly large, or as x approaches positive or negative infinity. We further extend the concept of limit to infinite limits, which are not limits as before, but rather a new use of the term limit. Infinite limits provide useful symbols and language for describing the behavior of functions whose values become arbitrarily large in magnitude. We use these limit ideas to analyze the graphs of functions having horizontal and vertical asymptotes. The symbol for infinity does not represent a real number. We use infinity to describe the behavior of a function when the values in its domain or range outgrow all finite bounds. For example, the function f of x equals 1 over x is defined for all x not equal to 0. When x is positive and becomes increasingly large, then 1 over x becomes increasingly small, right? So as x gets bigger and bigger in the function 1 over x, if x is a billion, then it's 1 billionth. If x is a trillion, then it's 1 trillionth. So as x grows, the function value 1 over x shrinks. And you can kind of see that in the shape of this graph. As x goes to infinity, the value of this function is getting increasingly small. When x is negative, its magnitude becomes increasingly large. So as x becomes increasingly negative, so the magnitude means like the absolute value of that negative number becomes increasingly large, then 1 over x again becomes small. We summarize these observations by saying that f of x equals 1 over x has limit 0 as x approaches infinity, or as x approaches negative infinity, or that 0 is a limit of f of x equals 1 over x at infinity and negative infinity. Here are precise definitions. All right, the precise definitions we're talking about. We say that f of x has the limit L as x approaches infinity, and write it this way. So it's the same kind of notation as before. If for every number epsilon greater than 0, there exists a corresponding number m, so it's using m here, such that for all x, for x greater than m, that would imply that, or lead to the conclusion that, the absolute value of the difference between f of x and L is always less than that epsilon. So you can again think of this as the skeptic challenge. So the skeptic says, I bet that you can't make the difference between f of x and this value become less than a billionth. And you say, well, if I get x big enough, if I find a big enough x bigger than this number, it'll make the difference between those two things be less than a billionth. And the skeptic said, what about a trillionth? And you say, well, I bet you I can find another even bigger value for m, that as long as x is bigger than that m, then the difference between f of x and that limit value is even less than a trillionth. And you can always imagine smaller numbers for epsilon, which makes then you have to imagine larger numbers for m, and that can always be the case. And that's what an infinite limit is about. All right, and it works the same way for negative infinity, except that instead of trying to find the number that x has to be greater than, so like a unimaginably large number, you try to find a number that x has to be less than, so an unimaginably large negative number. All right, let's look at the limits at infinity of rational functions. To determine the limit of a rational function as x approaches positive and negative infinity, we first divide the numerator and denominator by the highest power of x in the denominator. The result then depends on the degrees of the polynomials involved. So here's an example of what they're saying you should do. Let's take a look at what happens here. They're saying so the highest exponent in the denominator of x would be x squared. So we're going to divide every term by x squared. You divide this by x squared, you divide this by x squared, divide that by x squared, and so on. And you end up with all this. So that cancels and that cancels. So you end up with 5 plus, and then this reduces to just 8 over x This becomes just 3 over x squared. This one reduces to 3. This one just becomes 2 over x squared. And then you gotta kind of then just imagine x going to infinity. So x is becoming increasingly large. As x becomes unimaginably large, this becomes unimaginably small. This becomes unimaginably small. This becomes unimaginably small. So that's where they get these zeros from. These two terms, however, just stay as they are. So you just end up with 5/3. Now, that makes for a very simple way to do these kinds of problems that we don't have to. It just kind of proves to you why this is the case, but it leads to a very simple result. Whenever the degrees of the numerator is equal to the degree of the denominator, so that the degrees of the numerator and denominator are equal, the limit as x approaches infinity will always be the ratio of the leading coefficients. So the leading coefficient on top is 5, the leading coefficient on the bottom is 3. So the ratio of those would be 5/3, and that will always be the limit as x approaches infinity when the degrees are the same. It will also be the case as x approaches negative infinity, because if x approached negative infinity, this would still go to 0. This term would still go to 0. This term would all these would still go to 0. You'd still be left with 5 over 3. So it's still going to be 5/3. And that's going to happen every time the degrees are the same. All right, let's look at the next part B here. All right, we do the same strategy. We put each one of these over x cubed. And you end up with this. The x over the x cubed reduces to 11 over x squared. That becomes 2 over x cubed. This cancels out and just becomes a 2, and this becomes 1 over x cubed. Now, as x approaches negative infinity, we're dividing by larger and larger magnitudes, which means this goes to 0, this goes to 0, this goes to 0. So you're left with 0 plus 0 over 2 minus 0, which would be 0 over 2, which would still be 0. And that's also going to kind of leads us to a very simple conclusion that we can follow for this situation. Whenever the degree on bottom is higher, the limit as x approaches infinity or negative infinity will always be 0. Okay, we've got two very simple rules so far, so you don't have to follow this procedure if you just know these two simple rules. If the degrees are the same, the limit will be the ratio of the leading coefficients. If the degree on bottom is higher, the limit will be 0 every time. All right, this can lead us to something about horizontal asymptotes. If the distance between the graph of a function and some fixed line approaches 0, as a point on the graph moves increasingly far from the origin, in other words, as the magnitude of x gets larger and larger in either direction, we say that the graph approaches that line, the line of that value, that fixed value. It approaches that line asymptotically, and that the line is an asymptote of the graph. In fact, we would say that it is a horizontal asymptote. Like, for example, 1 over x, as x approaches infinity, that limit is 0. Same for negative infinity. Therefore, y equals 0 is a horizontal asymptote of the graph of 1 over x. All right, remember this example here where we got 5/3 as the limit. We can also see that graphically, that as x gets bigger and bigger, this function asymptotically approaches 5/3, the value of that function does. Whether you go farther and farther to the right, or whether you're going farther and farther to the left. You can even see that one for part B graphically as well. Remember, the limit of this one was 0, and you can see graphically as it goes to the right, the function is getting closer and closer to 0, and also the same way on the left. Let's look at example 4. Example 4 is not exactly a polynomial because of the absolute value bars there, but it's still going to have kind of a similar result, a little bit similar. We see that the degrees are the same, so we would expect maybe something to happen like the ratio of the leading coefficients, so maybe like 1/1. But because this is not a polynomial, we kind of have to follow the procedure as before. We're going to calculate the limit for the positive infinity and see what happens there, and for the negative infinity and see what happens there. So let's, for x greater than 0, for x greater than or equal to 0, the absolute value of x cubed is going to be the same thing as x cubed. So we can just remove the absolute value and do it like this, and then divide each one of these by x cubed. Okay, what do we end up with? That cancels, you're left with 1, 2 over x cubed. That cancels, you're left with 1, and 1 over x cubed. So that's going to go to 0, that's going to go to 0. So you're just going to get 1/1, which is 1, like we expected. But because of that absolute value, let's see what happens when it's negative infinity. What does the absolute value of x cubed act like when x is negative? When x is negative, the absolute value of x cubed will act like negative x cubed, right? Because let's say if x was negative 2. All right, the absolute value of negative 2 cubed would be the same thing as positive 2 cubed. All right, so if we make it be negative x cubed, that's going to make that happen because it would be negative 2 cubed, which would make it be positive 2 cubed. So that is a way to get the absolute value bars out of the situation, so we can do it like a polynomial. So we just replace this for when x is less than 0, when x is negative, we can replace this with a negative x to the third power, and it'll act just like this. Then we divide them all by x cubed. Okay, and so now this one becomes a 1. This one, though, becomes a negative 1. And this is still 2 over x cubed and 1 over x cubed. So this goes to 0, this goes to 0, and we end up with 1 over negative 1, which would be negative 1. So this was kind of a strange one where the limit as x approaches positive infinity is 1, whereas the limit as x approaches negative infinity is negative 1. We can see that in the graph over here. The graph of this function shows that to be true as well. As x gets bigger and bigger, the value of the function approaches 1. But as x gets bigger and bigger on the left, the value of the function is approaching negative 1. Let's look at example 9 here. Find the limit as x approaches infinity of this one. So look at these two terms. This is not a polynomial, so we can't really think of it that way. But this term obviously goes to infinity as x approaches infinity. This term, you get an increasingly large number under this radical. So the square root of an increasingly large number is an increasingly large number. So this also goes to infinity. So you kind of have an infinity minus infinity situation. What is infinity minus infinity? It's kind of, I don't know what to say about that. This is where infinities kind of blow our minds and produce logical contradictions for us. They defy our logic. But there's an algebraic trick we can do to figure this out. So the algebraic trick is to multiply this by its conjugate. And we do it as a numerator and denominator. So the conjugate of this, x minus the square root of something, would be x plus the square root of something. So they're multiplying it by x plus the square root of that, and x plus the square root of that on top and on bottom. So this is like over 1. So you're multiplying this with this, but this just multiplies with that. So if you multiply this as a conjugate, let's see what happens. X times x is x squared. X times the positive of that would be plus x square root of x squared plus 16. And then negative square root of x plus 16 times x is minus x square root of x squared plus 16. And then this thing times itself would just be, it's the thing under the radical. It would be, and it's a positive times a negative, so it's minus x squared plus 16, right? The square root of 3 times the square root of 3 is 3. That's kind of just the same concept there. And a positive times a negative made it this have to be a negative, and I need to make sure to apply that negative to the whole thing. Now obviously these terms in the middle cancel out. This becomes x squared minus x squared minus 16. That cancels out. So what do we end up with? We end up with negative 16 over x plus the square root of x squared plus 16. Okay, patiently we wait for what that means. Now let's imagine x approaching infinity. What happens to this term? It gets really, really large. What happens to this term? This is also getting really large. It's the square root of something really large, which is still something really large. So large plus large is even larger. So we have negative 16 over basically something infinitely large, which means this goes to what? This goes to 0. So this whole limit then, we've just proven it to be 0. On example 10, we have another rational function that is just involving polynomials on top and bottom. But this is a situation we haven't yet addressed. We've addressed when the degrees are the same. We've addressed when the degree on bottom is the highest. We have not addressed when the degree on top is higher. So when the degree on top is higher, I'm going to show you a kind of a trick that we can do there. All right, we're going to have to divide this thing with long division. All right, so hopefully you've seen long division before. If not, this is going to seem pretty tough. So we're putting this polynomial inside of this division symbol, and if we're missing a term, like where there's no x term, we need to put in a placeholder. And then we have 2x minus 4 out here. All right, then what we're doing is we're just taking this and we're saying x squared divided by 2x. X squared divided by 2x. All right, the x's reduce each other. You end up with x over 2. So we say that's x over 2. Okay. And then we have to, just like we do in regular long division, take what we put up here and multiply it by these two terms and write it below these. So x over 2 times 2x times x over 2 gives you x squared. Then x over 2 times negative 4 times x over 2 is negative 4x over 2, which reduces to negative 2x. So minus 2x. Okay. And we're subtracting that. We distribute that minus. And that will go away, and this will become 2x. And I bring down the minus 3. And then you say 2x goes into 2x how many times? Or 2x divided by 2x is what? So that's going to be 1. So you say plus 1. Then you take the 1 and multiply it by this and write it down here. So 1 times 2x minus 4 is 2x minus 4. distribute the negative. 2x plus negative 2x is gone. Negative 3 plus 4 is 1. And there's nothing left to bring down, so this is the remainder. So then my final answer will be x over 2 plus 1 plus 1 over 2x minus 4. Right, because anytime you have a remainder, you can just put that remainder over the thing you're dividing by. This term here, though, if we think about this remainder term as x grows increasingly large, this bottom part is getting really, really large, which makes this whole term go away. So that means that as x approaches infinity, or negative infinity, the limit of that of x squared minus 3 over 2x minus 4 will equal that oblique asymptote. It's called an oblique asymptote. It's a line. So I could also rewrite it if I wanted to as 1/2 x plus 1. So this is the equation of a line. And let's look at it graphically back here on when we look back at the book. If we look at that on the wrong page, let's see if I can find it. Here is the function, and it has this what's called an oblique or slant asymptote. You can see that this function value gets closer and closer to the value of this line as x gets larger, or as x gets larger to the left, it's also that way. All right, next subtopic is infinite limits. Let's look again at this function f of x equals 1 over x. As x approaches 0 from the right, so if x is a really, really small positive number, so like imagine x being like 1/1,000,000th, then it's 1 over a billion. Keep, change, flip, you end up getting a billion as the result. So as x gets increasingly close to 0, but on the positive side, the result of this is getting closer and closer to positive infinity. In other words, the value of f grows without bound, eventually reaching and surpassing every positive real number. That is, given any positive real number b, however large, the values of f become larger still, so as large as you can imagine. All right, if we approach 0 from the left, imagine putting in really, really small negative numbers like negative 1 over a billion, negative 1/1,000,000th. So 1 over negative a billion would keep, change, flip, give you negative a billion. So as you approach 0 from the left, you're going down to negative infinity for the function value. Okay. We are not saying that the limit exists and equals the number negative infinity. There is no real number negative infinity. We are describing the behavior of a function whose limit as x approaches 0 from the left does not exist because its values become arbitrarily large and negative. In other words, you can, whatever number you imagine, you can always imagine a bigger one or whatever. I think they go a little farther than I would want to by saying that infinity doesn't exist or something. I think infinity certainly is if we can imagine it and it's a concept that's useful, then saying it doesn't exist is not an accurate statement. It goes too far. But anyway, we can do the same thing to this example 11. As x approaches 1 from the positive side, this thing is it's just a really, really small positive number. So 1 over a really small positive number is a really big positive number. So as x approaches 1 from the right, the limit of this thing is infinity. All right. This is a really small negative number on bottom. So 1 over a really small negative number is a really big negative number. So as x approaches 1 from the left, this is going to go to negative infinity. And you can also see that graphically occurring here as well. So if we're close to 1 on the right side of 1, we can see this graph soaring up to unimaginable heights. And if we're on the left side of 1, we can see this function plunging down to unimaginable depths. All right, look at this one, 1 over x squared. If we, it says as x approaches 0. So if we're approaching 0 from the right, then this is an unimaginably small positive number, which makes this 1 over that thing be an unimaginably large positive number. As we approach x from the left, so a really unimaginably small negative number, when it gets squared, it becomes positive, an unimaginably small positive number again. So again, 1 over an unimaginably small positive number is an unimaginably large positive number. So whether we approach 0 from the right or the left, you can see this graphically, we're going to positive infinity as a result. So the limit of that thing would be, as x approaches 0, would be infinity. And it's the same on both sides, so it's a two-sided limit. All right, let's look at example 13. Here, if we can simplify the function and find a function that is equivalent to this, then we can do the limit more easily, and we can because this bottom will factor. It factors as x minus 2 and x plus 2. So this x minus 2 will cancel with one of the x minus 2's up here, and we just end up with x minus 2 over x plus 2. Now we plug in 2, and we just get 2 minus 2 over 2 plus 2, which is 0 over 4, which is 0. All right. Let's look at this one. So this time we factor the bottom. We get x minus 2, x plus 2. That cancels, and we're left with 1 over x plus 2. And if you plug in 2 now, you get 1 over 2 plus 2, which is 1/4. So these aren't really infinite limits anymore. This is kind of just a different topic. As it says, these examples illustrate that rational functions can behave in various ways when the denominator gets near 0. It can go to infinity, or it can have a hole in the graph, or it can not exist if it goes to different places and such. Let's keep doing these examples. All right, here we kind of already can think about what's going on here. Let's see here. So if x approaches 2 from the right, so x is like 2.01. That means this is going to be a negative number on top, like some sort of negative number on top. And on bottom, this is going to be something a little bit more than 4 minus 4. So a small, a small positive number. So if you have a negative number over an extremely small positive number, you're going to go to negative infinity. Right? Any negative number over an unimaginably small positive number, a negative over positive is a negative, so it's going to be negative infinity. All right, let's try it. What happens here? At this time, we're approaching 2 from the left side, so this is going to be a number a little less than 2, like 1.99. 1.99 minus 3 is, again, a negative number. But this time here, we're going to be a little bit less than 4 minus 4, which is going to be a really small negative number. Small negative number. So a negative number over another negative number is going to be a positive number. And it's something over something extremely small, which turns into something extremely large, so it's positive infinity. All right, part E. So that means that if we approach 2 from the right, we get infinity, negative infinity. If we approach 2 from the left, we get positive infinity. That means it doesn't approach a single value, So the overall limit then, overall limit on part E does not exist. All right, let's look at F. All right, we got 2 minus x over x minus 2 cubed. Well, 2 minus x is the same thing as negative x minus 2, right? If you factor out a negative, the x becomes positive, the 2 becomes negative, and you can rearrange it, it becomes x minus 2. So then we got an x minus 2 canceling with one of these x minus 2, so it just becomes squared. So we have negative 1 over x minus 2 squared, the limit as x approaches 2. So what we have is we have a negative number. So a negative number on top. And on bottom, what do we have? We're approaching 2. So if it approaches 2 from the right, that's going to be a little bit bigger than 2. Very small number. Sorry, it's going to be this is going to be a little bit bigger than 2, so it's going to be a very small positive number. If we approach 2 from the left, that's going to end up being something a little bit less than 2, which is going to make this be negative, but we're going to square it. It's going to become positive anyway. So whether we approach 2 from the right or the left, this is going to get squared, so it's going to be a really small positive number. So a negative number over a really small positive number is going to be negative infinity. Let's take a look at example 14 here. Let's do where we divide each of these by the highest degree x in the denominator. So I'm going to make each one of these become be divided by an x squared term. All right, and let's simplify it so it becomes on top 2x cubed minus 6x squared plus 1 over x squared. So I'm just reducing these, x to the fifth over x to the second reduces to x to the third because you subtract their exponents. All right, this on the bottom we just x squareds cancel. We just have 3 plus that x cancels with that x squared, and you're left with a 1 on top and an x on the bottom. So 1 over x minus 7 over x squared. All right, now think about this as x goes to negative infinity. As x goes to negative infinity, 1 divided by a huge thing, even if that thing is negative, it gets closer and closer to 0. This goes to 0. This goes to 0. So we're left with we're left with 2x cubed minus 6x squared over 3. Okay, if we put negative infinity in there, negative infinity cubed is going to be negative infinity. If we put negative infinity in there, negative infinity squared is positive infinity, but it's minus positive infinity. So we have negative infinity minus infinity, which is still even more negative infinity. So this thing goes to negative infinity. So the answer to this limit, the limit of this function as x approaches negative infinity, is negative infinity. All right, let's look at example 16. Find the horizontal and vertical asymptotes of the curve. So horizontal asymptotes will be found as x approaches positive and negative infinity. Vertical asymptotes will be found when the denominator is 0, so as x approaches negative 2. So we can go ahead and know actually that we have a vertical asymptote at x equals negative 2. And the reason is because the x plus 2 doesn't cancel out with anything on top, so if it did, it would be a hole in the graph, but since it doesn't, it's a vertical asymptote. The horizontal asymptote, if we plugged in infinity here, if we plug in infinity, we get infinity over infinity. And I think I've already told you this earlier in this video, but if your degrees are the same on top and bottom, and these are just polynomials, so we can use this rule, the horizontal asymptote is going to be located at the ratio of the leading coefficients, which is just 1 over 1. Right? Leading coefficient is 1 there and 1 there, which is just 1, so that we have a horizontal asymptote at y equals 1. Once again, on example 17, we're finding horizontal and vertical asymptotes. Horizontal asymptotes are when x approaches positive and negative infinity. Vertical asymptotes is when the denominator is 0. So in this case, if we solve that denominator, we would get that the denominator equals 0 when x is positive and negative 2. So those would be the equations of our vertical asymptotes. We have a vertical asymptote at x equals 2 and another one at x equals negative 2. Horizontal asymptotes, we plug in negative infinity, and I think I've already told you this as well, but if the degree on bottom is higher, then the horizontal asymptote is just going to be 0. So, and you can know that again because this bottom thing is going to go to infinity. So it's going to be anything over infinity, even if it's negative. Anything over infinity goes to 0. So our horizontal asymptote will be y equals 0. So this is what that looks like graphically. We had a vertical asymptote at 2 and at negative 2, and we have a horizontal asymptote at 0. Let's see if we can figure this one out. All right. The limit as x approaches 0 from the positive side of ln of x. Let's just think about ln of x. All right, I guess I'll show you this kind of in a quick way first, if you can remember what this graph looks like. Oh, it ain't like that. Let me fix that. It is like that. And you can even see that it has a vertical asymptote right here. And so as x approaches 0 from the right, where's this, the limiting value of this function will be going down to negative infinity. So you already know it's going to be negative infinity, but let's look at it algebraically as well. What does ln of x mean? I always teach this in college algebra this way. Maybe you got a similar teaching in your high school classes about this. A log, anytime you're doing a log, which ln is just another log, it means the exponent on something. The exponent on something. Here it's the exponent on what's understood. What's the understood base right here? The understood base right there is e, right? That's what ln means. So here it means the exponent on e. That gives you x, or in this case, that gives you 0. So we can rewrite that and think about it like this. E to what? E to the what gives me 0. What would I raise e to get 0, or to get close to 0? What if I raise e to anything positive, it's just getting bigger. But what if I raise it? What if I raise e to the negative 1? That's 1 over e. If I raise e to the negative 2, that's 1 over e squared. If I raise e to the negative 3, that's 1 over e cubed. So we're getting smaller, right? So then what should I put right here to make it get as small as you can possibly imagine? Well, the smallest would be negative infinity. It would be 1 over e to the infinity, which would be 0. All right, so the limit of this as x approaches 0 is negative infinity. Let's see if we can find the vertical asymptotes of these trig functions. All right, remember, vertical asymptotes happen when the denominator equals 0. So since secant of x is 1 over cosine of x, it would happen when cosine of x equals 0. So where does cosine equal 0? You could do the arc cosine of 0 to figure that out in your calculator, but if you kind of just remember some trig, cosine is the horizontal component. Cosine is the horizontal component of the angle here. So if we're at 90 degrees or at 270 degrees, our horizontal component is 0. So we could say x equals 90 degrees and 270 degrees, 90, 270, and back around again to 450, and back around again to it. So every multiple of 90. So I'm just going to say 90 degrees plus or minus 90 degrees times some integer n. Or if you wanted to do it in radians, it would be pi over 2 plus pi over 2n, where n is any integer. What about the next one, tangent? Well, it's going to be exactly kind of the same thing here because it's got the same denominator. So it would also have the same vertical asymptotes as that one. So same answer. All right, let's look at this problem here, number 20. So it says we have this function f of x, 3x to the fourth minus 2x cubed plus 3x squared, blah, blah, blah. And g of x is just 3x to the fourth. So notice 3x to the fourth and 3x to the fourth are the same, but all these other terms in f of x are obviously different. It wants us to show that although f and g are quite different for numerically small values of x, small is a relative term, they are virtually identical for the absolute value of x being very large, again, that being a relative term, in the sense that their ratios approach 1 as x approaches infinity or negative infinity. All right, I'm going to go ahead and tell you the reason this is going to be true. The reason this is true is because for polynomials, the highest degree polynomial will always be the dominant term. It will dominate all the others when x gets large enough. When x gets unimaginably large, this gets unimaginably larger than all these others put together. So, and we can show that algebraically now. Let's show it algebraically. We can show that by, they actually follow a very good process here. If you divide this whole thing by 3x to the fourth, like divide it by this first term, and then just kind of simplify everything, that becomes 1 minus this plus this, and so on. All these terms go to nothing, right? So you're just left with 1. So the ratio of f of x over g of x goes to 1, which means those terms, that whole thing, the whole f of x and the whole g of x, are becoming the same thing if x gets large enough. So f of x acts just like g of x for large values of x, or in other words, as x approaches infinity. So you can see, let's look at the graphs of these guys. So you can see here's f of x and g of x, f of x being this blue curve and g of x being this pink curve or red curve, whatever color that is. You see they have, the values are obviously different values here in relatively small numbers, but as the numbers get bigger, you can see that the curves are are getting closer and closer to one another as x gets larger. All right, here's a summary. In this chapter, this is a summary of all of Chapter 6, we presented several important calculus ideas that are made meaningful and precise by the concept of the limit. These include the 3 ideas of the exact rate of change of a function, the slope of the graph of a function at a point, and the continuity of a function. The primary methods used for calculating limits of many functions are captured in the algebraic limit laws of Theorem 1 and in the sandwich theorem, all of which are proved from the precise definition of the limit. We saw that these computational rules also apply to one-sided limits and to limits at infinity. Moreover, we can sometimes apply these rules when calculating limits of simple transcendental functions, as illustrated by our examples, or in cases like the following. The word transcendental function is just a fancy word for pretty much other functions that aren't polynomials, like sine of x, or e to the x, or natural log of x, or something like that. Functions that aren't polynomials are known as transcendental functions. So next, we're going to talk about the derivative is exactly the tool we need to calculate limits such as these. And the notion is the main subject of our next chapter. So, chapter 2, I'm just going to go ahead and tell you, chapter 2 is not the most enjoyable chapter for me either. It's a lot of theory and abstract thinking, which is, in a way, cool, but in another way, not as enjoyable as when you can put something into more concrete, applicable terms. Once we get to, we kind of had to lay this foundation in chapter 2. But once we get to the derivative stuff in chapter 3 and the integral stuff in further chapters, it's going to get more concrete. I'm going to enjoy it more, which probably means you'll enjoy it more. And it'll be much more applicable and hopefully more satisfying to us as well. All right, last thing I want to do in this video is just go over a few homework problems as I'm going through the homework to show you just some things I think you might struggle with most. 1 through 3 looked very doable. Number 4 I thought might be confusing, but here's how we can do it. If we put infinity in for this, like what is the sign of infinity? It's kind of impossible to know, but here's what you can know. Like, what's the biggest value that you get for sine? Sine is always going to be between 1 or negative 1. What's this going to become? It's going to become infinity. So it's like 1 or something smaller than 1 over infinity, which is 0. So the answer to that is 0. Let's take a look at this homework problem. It's 2.6.25. It may be number 8 on your homework, or it may not be number 8. I'm not sure. But how do we do this one? I would say we should go ahead and take what's in here and divide every term by the biggest degree term in the denominator. So that would give us 1 over x squared minus x cubed over x squared over x squared over x squared plus 4x over x squared, and reduce all that. So it becomes 1 over x squared minus x over 1 plus 4 over x. And as x approaches infinity or negative infinity, these terms are going to go to nothing. So you get negative x over 1. Now plug in negative infinity for x, and what do you get? Plug in negative infinity right here, and you get infinity, right? Infinity over 1, or just infinity. And then infinity to the 7th power is infinity. So this limit should be infinity. Okay, what about this one? 2.6.27. Think of this term as 1 over x to the 8th. And so as x goes to infinity, that term's going to go away. So just think of this as 4 square root of x over 2x minus 2. And as x goes to infinity, x, the square root of x is the same thing as x to the 1/2. And I believe I've told you that if the degree on the bottom is higher, then it's going to go to 0. This is going to grow much faster than this because the degree is higher. So because this grows much faster on the bottom gets a lot bigger than the top, and so this is going to approach 0. And if the top were the higher degree, it would probably approach infinity. Because the top would grow much faster than the bottom, so you'd have a lot bigger number over a lot smaller number, so it would be approaching infinity if that were the case.
Let's think about this one. As x approaches 7 pi over 2 from the negative side of it. So remember tan is sine over cosine. So I'm thinking like, what is sine of pi over 2? Sine of 7 pi over 2. Let me go over here and look. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So sine of that will be -1. What is cosine of this? Cosine of 7 pi over 2 is going to be 0. But what is it when I'm like just barely at it, like there? What is the horizontal component of an angle, like almost there? Well, it would be really close to 0, but it would be a small negative number. Right, because the horizontal component over here is negative. So it would be a small negative number. So we got a negative over a really small negative, which is going to be a negative over negative is positive, and since it's over an unimaginably small number now, this is going to go to infinity. And it will be positive infinity because we got a negative over a negative, which cancels out and makes a positive. So this whole thing is going to infinity, and so 2 times that is still infinity. So the answer to this one should be infinity. Another way to approach this problem, if you wanted to, if the algebra was kind of stumping you a little bit, you could graph 2 tan x in your calculator, like put that in for y1, and then when you graph it, hit zoom and then go to zoom trig. And if you go to zoom trig and make sure you're in radian mode, then it's gonna draw the graph, and the dashes are going to be like pi over 2 pi, 3 pi over 2, 2 pi. That's what the dashes will be, those numbers. And so you can look at 7 pi over 2 just a little bit to the left of it and see where is that graph going. Is it going up to positive infinity or down to negative infinity or what? And you could tell what the answer would be graphically. All right, let's look at this one. This is 2.64.51. Cosecant is 1 over sine. So as theta approaches 0, what is sine of 0? We could even look at this on the graph, right? Here's what is sine of 0? It's 0. But what if we're just a little bit past 0? No, just to the right of 0, then we're a really small number. So 1 over a small positive number is going to go to infinity. And 3 plus infinity is still infinity. So this should be infinity. Number 17, or 2.6.57, I'll just give you a big hint on this one. Go ahead and factor the top and bottom and cancel out the common factors and make this function simpler before you try to do this. It'll make your life a lot easier on that problem. I think that's going to do it for section 2.6. Good luck on that homework. Let me know if you need help. I'll see you next time.